I would otherwise write here, similar to what happened when we discussed the implementations. Only that I will write in uh, on the document rather than in comments on the code editor. First off, does everyone hear me well? Yeah, great. That's perfect, I guess. So today we will talk about Mohs algorithm, which I don't think is that very, which unfortunately one doesn't see that often, I think. But it's particularly important to understanding rather how uh, SQRT behaves when it comes to programming problems, and it's a very good example of why we need an SQRT-like approach. Uh, okay. To start off, I'm not sure if you've read all the problems that I otherwise sent. Uh, wait. Uh, okay, but at the core, Mohs algorithm tries to solve the following problems. So, given Q queries, but importantly offline, um, of the type L to R, solve the following problem. Uh, Aggregate information from L to R to compose uh, the, the given query. Normally, what I say here is quite simplistic because technically this applies for most data structure like problems. Because, for example, segment trees, if I'd have a query of the type from L to R, aggregate information, but when I mean by aggregate information is take the sum from L to R, uh, then uh, yeah, aggregate means compose, yeah, accumulate basically. Um, so if we are to solve the problem of aggregating the sum of or getting the sum from L to R, we know that this can be solved with Fenwick trees or segment trees or so on. And such examples are examples of information that is easily manipulated and combined, importantly. That is, we can describe a monoid sort of uh, that acts on a very small set of numbers, or on which the set, the cardinal, not the cardinal, the size of the elements that are involved in the operation are quite small. I don't need to formalize that really because one would understand that. For example, if you need the sum of two elements, uh, sum of two elements only requires, the two elements. But where Mohs algorithm really shines is when this information is sort of difficult or weird to aggregate. For example, count the number of elements from L to R such that they have a frequency equal to something. K. How many elements from L to R appear? A number of k times. If we are to do this in sort of a segment tree, then we really need for uh, uh, we need for each node to be able to give the answer for that single node. But then the issue is how do we combine two nodes? Because normally in a segment tree, we'd have like uh, I'll draw here because this time I can draw it. In a segment tree, we know that the advantage of a segment tree is that we divide any query of the type L to R into a count of logarithmic uh, sub-intervals for which we answer the question. So you know that we solve the problem for L1 to R1 and also for L2 to R2, and that these altogether can be composed to get the information that we want for LR. So like we'd have these nodes, and if we are to compute the sum from L to R, we can just add the sums that we already calculated for these intervals. But now imagine I want the count of elements such that the frequency of x on that interval is equal to k. Then in this node, I may keep a list of values and their frequency. But then how do I combine it with the elements over here? I'd have to traverse at least one of the lists entirely from start to finish. And that is really not optimal. So in such a case, we can say that the um, the information to be combined is very heavy. So then Mohs algorithm addresses this, although albeit in an offline manner, um, by not using segment trees at all. Mohs algorithm assumes the following. We query data structure such that the following have to apply. So first, uh, insertion can be done in relatively small time. Two, uh, erasure can also be done in relatively small time. Third, we can erase random elements from the data structure. But this actually can be circumvented. But for now, let's assume that this is the case. What do I mean by random elements? We can erase random elements from the data structure is, for example, in a DSU. Maybe some of you know that from a DSU, you can't erase random edges that have been added. Only the uppermost edge can be deleted. That is, we can do what is called rollback. But if we are to, then the SU in such a case is not a data structure that is applicable. Although this can be circumvented, but I'll explain that later. It's unnecessary for now. So it is really important that we can erase any random element at any time we want. And that is it. These are the three properties that the data structure that we of a data structure that can admit a solution with Mohs algorithm. To be more concrete, I've given an example here of the count of elements x such that the frequency from x the frequency of does it work now? I'm really not sure why this happens. When did I get cut off? Like, I don't know. Okay. So for the problem that I discussed earlier, for queries from L to R determine how many elements have a frequency equal to K. So technically the queries of the form L, R, and K. We try to see if we can create a data structure that can solve this problem at least in oven time for any query, because we start with the data structure empty and then add elements one by one. Yes, someone raised a hand. Mike again. Wait, it tells me that it works. Now, does it work now? I have no idea what is going on. I really don't. Okay, please keep informing me when it is the case. So let's see if we can develop a data structure that can at least solve this problem. So if you want in oven time to answer just a single query of how many elements for a given segment have frequency equal to K. Obviously, to start doing this, we need to have a frequency array, which we notice respect the postulate that we've put forth, that any data structure that can admit association with Mohs algorithm needs to respect. But really, I sort of might have overlooked this a bit, and it's a bit irritating. This does not really solve the problem, because then the question is, how many elements of this array are equal to a value K? For this reason, we notice that we can technically hold another data structure on top of the frequency array, that is a frequency array. So, this keep a frequency array over the frequency setting elements. Now, this we have an f of x for which we increase the frequency. But before we do that, we trace the fact that the initial frequency existed. So then if x, for example, appeared 5 times, but we know that we are inserting an x, so it will appear 6 times, then the frequency of the frequency of 5, that is for how many elements exist such that they appear 5 times, obviously decreases because now this element will appear 6 times. And then with the newly found frequency, we increase it. And erasing cannot be erased. Instead of adding 1 to the elements here, instead of changing the frequency by adding 1, we delete it, but then the way that this behaves in the frequency of the frequency array is the same, because we initially had a frequency, but that changes, so we no longer have it, and then we have a new one, so we have to keep track of the new one. And also, obviously, that postulate also holds. Any element, so long as they're in the data structure, can be erased. We don't care that you might have inserted a 2 at the beginning or a 3 at the end. We can erase both of them. Delete old and add new. Delete old, delete the old value of the frequency and add the new value of the frequency. That's basically what happens. Okay, and pairing is the term ff of k. Such a data structure can solve the problem in both ends of the time. But we can find a way such that we will have a total of n, square root of n, insertion and erases, insertions and erases. And also, for every single query, we will have at one point a data structure to contain all the elements for that query. So what it essentially means is that we can find a way to let's first say that things that we have are the following. We have basically Q intervals, and we need to aggregate this information for each of them. What aggregate means is that we need to insert all the elements from Li to Ri, and no other elements should be inserted. We need to find a way to insert and delete elements from the array into the data structure or out of the data structure, such that at every point, at some point for each query, we will have those things inserted. See, these are the queries. One trivial way to do this, to keep a data structure that keeps inserting elements, erases elements, and so on, to have every single query represented at one point in the data structure would be pretty easy, actually. Because, for example, let's say this is the first query. And start by inserting all the elements in order. In the data structure, element 5, element 6, element 7, 8, 9, 10. After we do so, we can perform the query from L1 to R1. Then, to have the elements from L2 to R2, we notice that maybe we don't need to actually erase all the elements from this from the data structure, but we only need to erase all the elements that don't belong into the next query and insert all the elements that belong to the next query. It's not the case because we inserted in the data structure elements 5, 6, 7, 8, 9, and 10. To be able to answer to this query, which seems to be from 7 to 14, we have to erase elements 5 and 6 from the data structure and then insert elements 11 through 14 into the instruction. Then to solve the issue from to structure to answer from L2 R2 to L3 R3 to the third query, we need to erase all the elements that don't belong to the third segment. In this case, it's from 12 to 14. We need now to erase them. And insert all the elements that belong to L3 R3, but are not yet inserted. In such a case, it's all the elements from 6 to 2. It is clear what we are doing so far. So here, what I am trying to do. I think right now I maybe have gone too fast. So if there are any queries, please write them on the maybe document where you might not understand something or ask. To go over again, what we are trying to solve now is we assume that there is a data structure for which we know we can black box it as a thing that in which we can insert elements and in which we can erase elements. And essentially, any query from L1 to R1 just asks to insert all the elements from L1 to R1 or from that left point to that right point into the data structure. And after we do so, after we insert all of them, we know that we can query the data structure for the information that we want. I described here such a data structure that would answer the question for a query from L to R. Please tell me how many elements have a frequency of exactly k. How many elements appear exactly k times. This is such a data structure. And we can black box it. Furthermore, we don't need to consider how it works to insert things in it, how it works to erase things in it, or what it takes to query. We know that all of these three operations can be handled. And so the question is, how do we modify this data structure that is actually pretty rigid to answer queries of the form from L1 to R1? Please answer. Please have this data structure with all the elements from L1 to R1. From L2 to R2, please have this data structure have all the elements from L2 to R2, and so on. Please, if anyone has any questions, now is the time. No. Hooray. Thank you, Timo. As I said, this way of changing the data structure for an arbitrary of the elements, and please note the arbitrary, will perform actually all the n-squared operations. And that is pretty easy to see, because if we have queries like this, 1 to 2, and then the next one is from 16 to 17, and from 1 to 2 again, and then again from 16 to 17 again, and so on. what will essentially happen is that or let's make them a bit longer. Uh, um, if we keep repeating segments like this, and this is the order they are given in the input, and we don't care to reorder them or whatever, we notice that at first we need to insert like half of the elements, then we need to erase these elements, then we need to insert all the latter half, then erase it, insert the first half again, and so on. And this is pretty redundant, even if we imagine that maybe these queries are not so similar, but it's still part of the prefix. This is clearly redundant because maybe all of these first segments we could actually solve incrementally. For example, in this case, they are all prefixes. So then we can just, in such a case, we can answer all of them in O(n) time by inserting elements one by one in the prefix, and then when we get to an appropriate prefix, we just query the data structure for that time period. And similarly for those on the right. We shouldn't move the data structure from this state to this state back to a state that was very similar to it before, because that will inevitably take O(n) square time. Maybe not the approach that we've had so far is wrong, where we adapt the query from the ith query to the i+1 query by inserting elements that don't appear and erasing elements that shouldn't appear, but really the order of the query of how we consider queries to do so. As I previously said, let's assume there are many queries where Li is equal to Lj. So a set of all the queries where all the left endpoints are equal to some constant C. Let this set be yes. Then all the elements in S can be solved in one time. I hope everyone agrees with Vivid. What do you mean? The elements in S can be solved in O(n), as I previously mentioned, because we can initialize the structure with the element C, which is a common left point of all the elements in this set, and then increasingly adding elements to the right until we find that we covered all the laziness. So what we do is essentially, if these are the queries that we are asked, we will not solve them in this order, but rather in the order of their sizes. So at first we will try to solve this query. We see that we need to insert 4 elements, we do so. Then the next query that we will solve is this one. Having already inserted all of these elements in the data structure, we can now just insert what remains, and we will solve this query much faster. And for this query, we can just insert what remains and we will solve it much faster. And by the end, really what will happen is that we will insert every element from 1 to n exactly 1 time. This is horrible still, because if there aren't like a great number of queries where the left endpoint is equal, like maybe all the left endpoints are distinct in uh, the set of queries that we have to handle, then this is still horrible. This is still O of n, because then how do we solve the next set where the left endpoint changes? Maybe we can just erase the first element, and then the last state of the data structure includes all these elements. And we really wanted to include only these elements. So then still we need to erase about all of n elements. And maybe while we do so, we have to insert some other O of n elements, and then we move on to the next one and so on. This is still O of n. But it is actually O of n times the number of sets in which we, the number of endpoints. Is everything independent, so it doesn't, so that we can, if query doesn't affect the I plus one query, we can find answer for each query when we want. Yeah, that is also important. Sometimes in problems, it is the case that queries need to be solved. Okay, so there is a big distinction. There are two types of problems in data structure. There are offline problems and online problems. The distinction between these two is that online problems require that one would have a data structure that when it is asked to do a change, it will instantly do it. As offline problems actually are structures that can do queries in order. Online problems are more simply seen at the IOI, where they give you like a function query which you need to solve, like implement the function query from L to R, and you have to answer with query from L to R whatever they ask you. But offline problems are maybe more seen as things that appear when we have batch problems. That is, I'm giving you all the queries at once, like in an input file, for example, please solve them. One should assume every time that they see a problem, although not in IOI, because in IOI it's clear that they could give you an online problem every time they want. But in standard problems where you are given a file, basically a file to read the queries from, maybe one normally assumes that they'd have to answer the queries maybe online, because this is sort of natural maybe. But I tell you that let's see that every time you see a problem where you are given queries at once, you should instantly assume that you should try to solve it in an offline manner, to not really try to answer the queries one by one. Maybe you can reorder them. And Mo is like the forefather of reorderings, so to say. Online problems can also appear in other contexts, maybe also offline contexts, when you actually need a data structure that can be easily modified, for which you need to answer a DP. Like in the DP, like most notably, most familiarly is convex haltric. Although the queries are technically offline, you still need a data structure that can constantly adapt to every single update that you have. So that's I think important. So the new algorithm now effectuates n times the number of distinct left points. And this is a little hint, because we can actually try to reduce the number of left points to SQRT. some value b. And the question is how. What we can do is the following. Consider all the left endpoints from 0 to uh, some value b to be then all the endpoints from b+1 to b are also equal. So actually, obviously, if this is actually the case, then the problem is then actually really solved in O of n times n over b. So good. But the question is, the solution that we had before really ignored any work that would be done with the left endpoint, and so that we can adapt the data structure to answer for every right endpoint by increasingly adding new elements at the end. So increasing R, setting elements one by one, and that's some point for every query we'd have it answer. But we never saw anything done with the left endpoint, and now is the question, since obviously all elements from 0 to b are not equal, what do we do with the left endpoint? The answer is simple. We just modify the left end from one query to another within the bucket of b times I to b times so then if we imagine that these are these intervals that I've spoken about, then we forcefully say that every left endpoint that belongs to the same bucket, equivalent to every other endpoint that belongs to the same bucket. And for example, these queries will be solved in the following manner. So first, because we considered all of these segments to be equal, we sort them by the right end, because we said that we will solve the segment in order of the right end. Then we inserting right elements one by one for each such query. So initially, to get from this query to this next query, we need to insert so many elements at the right to get to this point. But since these two are obviously different because they don't actually share the same endpoint, we need to change the left endpoint to match with the new left endpoint. In such a case, we really only need to erase this value. And to move forward, we see that we need to insert these elements. We basically insert them, and then we notice that the left endpoint changes, and we need to erase this element to actually match with the new thing. And then we do the same thing here. And then we notice that there are some elements at the left that we need to insert that we didn't yet. So we also insert them. So essentially what we did is the initial solution where we modify the set of elements that we include from one query to the other. We notice which do not yet appear and which shouldn't appear, and we erase, we insert the former and we erase the latter. But then when we do this, okay, now because we have a clear idea of what we have, and this is the third we've made some sort of improvement or some modification. Let's actually analyze what the time complexity would be. So we know that for every single bucket that we solve, for every single query, the left endpoint might move about the positions. Because really, what is to say that the next query does not start from the leftmost element, and then the next one starts from the rightmost element. In such cases, we need to either insert or erase all the elements within the bucket, and we know that the bucket we said is of length B. So we might do the work it's of B per query. And what happens with the we know that initially the right endpoint starts somewhere, and then for every single bucket, we move it one by one, position by position, until the very end of the array. So for every bucket, there is of n work. That is of n over b times O of n. So the final time complexity is O of n squared over b plus, and this is important, it's q times b. And it is said that when b is equal to s square root of n, the final time complexity is of square root of n. There are a lot of caveats. We missed a lot of things. The first thing, before we go through these, it's sort of clear what the final algorithm is. N times n over b times b times n. No, because the thing is that every single query has O of b work. Because for every single query, we move it from left to right. And there are q queries, so that explains the b times q factor. Is that clear? Thing is that for every bucket, the way that we handle the right endpoint is sort of irrespective to the queries. Like we could have had 1 million queries for a single bucket, and we'd still do O of n work. We could have 10,000, no, sorry, 10 million queries, and we'd still do O of n work. Chances are that when this happens is because most of them have basically the same right endpoint. Although they might change in the left endpoint, they have the same right endpoint. So this is why O of n appears here, but O of q appears here because every single query is conditioned by the fact that we need to tweak the left endpoint a bit to the left, maybe a bit to the right, to actually make sense from one query to the next. So is the reasoning of why this time complexity is clear? And the general algorithm, or what happens? wasn't talking. So I think that explains it. It works now, no? So I try to uh, reiterate of what the actual algorithm is. One of the things we missed is that this complexity is not actually of n square root n, it's actually of n square root n plus q square root n. And maybe sometimes it is the case that the problem authors think they are very funny to set q is like 10, it's like 1 million, but n is actually like times, 5 times 10 to the power of 4. And obviously there is an imbalance between 1 million times whatever square root of this value is and times the same square root. Because this is much heavier, and we'd really like to have something like maybe of n square root of n plus q. So this factor isn't so heavy. What we did wrong here was to assume that b is equal to square root of n works very good here because q might be equal to n, and this value has its minimum. Normally, how to solve square root b plus q times b minimum of this for any b is by by differentiating the given function and seeing where time of b is equal to 0. And then in such a case, we say that we find the local minima, and then the local minima might also be the global minima in general or whatever. This is sort of math. I'm not going to bother you with it, only to say that technically the derivative of this function with respect to b is n square root over minus over b square root plus q. This needs to be equal to 0. So then what happens is we say that n square root over b squared equal to q. Then b is equal to square root of q over n over x squared. An easier trick whenever one will have to deal with such things is, as I said, technically there is an imbalance if we set b to be square root, because this will be greater than this. So a little trick to do is try to assume that every element in the complexity is equal to, then we have n squared over b equals q times b. So then n squared over q is equal to b squared. So then we actually have the same answer. And this trick also works for both functions, basically. Is that clear? So if we analyze furthermore, we will, let's see what the actual time complexity is in such a case. So n squared over b is equal to of n squared to the fourth over n to the second times q, which is of n times square root of q. And of q times b is equal to of square root of q squared times n squared over q. It's also of n times square root of q. So final time complexity Yeah, so yeah, in cases when q is equal to n, clearly, as I've shown here, the time complexity is n times square root of n if q equals n. But I just mentioned there might be cases when this is not true. It's just not true. When q is not equal to n. Another such case is whatever happened to the data structure that we had before. Because you might know that data structures are not in general just arrays or frequency arrays where we just plus one an element and that's it. Maybe not all operations are of uh, hmm, wait, I forgot what uh, I forgot where I was actually going with this. Only to say that sometimes, but I can't really point to any specific time. It might be the case that uh, some of the operations that we have over here would, some of them might have a log factor and some might not have a log factor. But what is a very simple example of this, and I think it's one of the problems that we sent is when queries are not really, so to say. So this basically means the following thing. If we have a data structure that can insert arrays in of log n and query in of log n, which is most data structures, like sets, whatever. Then the time complexity is of n times square root of q times n plus q times log n. We completely so far ignore the fact that there is this q factor. It's for the queries. Okay. But in many cases, so okay, what the issue here is that obviously this factor we do not care for it. It's very small compared to this. What we really have to do with is we have of n times square root q x and very few things. Maybe we can afford to do slower queries and much longer, much shorter updates. That is from ovlog update with ovlog queries. We can maybe and the data structure such that updates are of one, but queries are of square root. In such a case, we remove the log n from here and we put square root over here, which might be optimal. Is everything sort of clear so far? So things that might happen. If so, one of the problems that I've intended to cover in this lesson. What happened? Okay, so I said that maybe the data structure that we really want to use for the segment 3 would Like normally, the most natural way to think about it would be would be a data structure where we can insert and erase in O of log n and query in O of log n. But such data structures are bad in general because then we'd have a very big imbalance in the time complexity. We'd have n times square root times log, but queries are effectuated basically immediately. And we think, can we sacrifice time done on queries while keeping the updates very short? And it is important to think that because maybe it really depends from case to case that we can find a data structure that instead of the most natural way to do it, which involves log for insertion and log for log for updates and log for queries, to have instead of one per updates, which are really the heaviest thing that we have, and then of square root per queries. We like there isn't a universal formula of how to do this, but it's important to keep in mind that the heaviest thing and the worst thing at the most in most algorithm is updates, and we should do our best to keep updates as small as possible. Again, it depends, but I don't think in general it really depends that much. It's this. It's calculated when we consider that both the two factors that we have in the time complexity, and this is number of updates. We either calculate the derivative of this function with respect to b, or we just consider that the two values should be equal. And if the two values should be equal, then we get this formula. Is that clear? Okay, so for this problem, for which you again need to select the English translation of I'm not sure if Shohrukh showed it to you yet, or if not, if you need to take some time for you to read it. Okay, so I think we can start with the solution. Does anyone have any ideas they would like to share or discuss? Okay. If not, just get to it. Uh, so the problem asks us to find a super. I don't know. I'm not sure why they call it a subinterval. I think it's pretty stupid. Is it? No. Yeah. Uh, Bad translation because it's not a subinterval. It's a super interval. That is, it needs to contain everything that we have in the sub. In the So we get a query LR and we need to contain it needs to contain everything from it, really. So then we imagine that if we were to solve a Mo-like problem, then normally, as I said, Mo says tells you how to move from one query to another, or in which order you should move two queries to another, such that at every time you keep the set of elements from that interval inserted into the data structure. But in such a case, because sort of we need to handle everything outside it, we will later see that this actually means that we need to move from one query to the other, such that the elements, such that for every interval, we actually erase every single element from the data structure that is included in that interval. So that also works technically. Now, a small caveat on what XOR is, I think. If an interval, so from VL to VR, has some XOR sum equal to 0, then that's it. That's what it means. But it generally is helpful to associate this with partial sums. Yeah, you might be familiar with like partial sums, which tell you that not the XOR sum, but the actual sum from elements from L to R. There we calculate like Si equals the sum of elements from 1 to that I. And then to get the sum from L to R, we take the sum of R and erase the sum behind it. We subtract it. But when it comes to XOR, we can just XOR by that value. And if we really want to calculate, if we want to check whether an interval has XOR 0, it really means that when we XOR the two partial sums, we get 0. But that's equivalent to the two partial sums in the endpoints are equal. So then we can reshape the problem to the following idea. Given a set of numbers, an array of numbers, C1, C2, Ci, Cj, Cn, determine for an interval that is given like this, Lr, the shortest length of any interval that contains it, such that we can adjust this to be the actual endpoints, but whatever, such that the values at the endpoints are equal. Wait, Timur wrote. I think what you can do is create a prefix or yes, and changing the problem to finding equal elements outside the given which have the shortest distance. Yeah. Sorry, I didn't get to see that so fast, but I think you are confirmed that your idea is correct, as I've explained here. Good. So then, should we do? Okay, let's really try to find the shortest uh, length of a segment whose, whose endpoints have a value equal to a constant c. So then, what does it mean to shift the interval from, like, let's say from L to R to L to R plus 1? What does it mean to try to solve this problem? In such a case, if R plus 1 was equal C, it is no longer suitable. Similarly, if we go from LR to L minus 1 R, still delete L minus 1 from data structure. Similarly, if you actually shorten the segment, as I previously said, this actually behaves like what we described as an insertion effect. Okay, so what is this data structure that we need to keep? Well, if we keep a stack of all the indexes that are suitable endpoints on either side, then the data structure is the following. Insertion in data structure, so basically the opposite of what happens here. So stately insertion is add an element at the top of the stack. Either the left one or the right one. Arrays pop an element from and query return the difference between the two endpoints of the two stacks. So that maybe if we have like a segment here and we want to consider all the values Cj such that they are equal to capital C, well, I think lowercase c is like that and capital is without the little tail, but whatever. Let's say that they are at these positions. So clearly, if we want the minimum segment whose endpoints are equal to C to include this segment, we have to take the rightmost element on the left and the leftmost element on the right. And these two are undoubtedly the candidates for the best segment. If we are to expand the segment further left, we might notice that this element will get contained in the segment and is no longer suitable. So in that case, we need to move the candidate right pointer a bit to the right, that is to the next value. If the same thing happens because we'd extend the segment to the left, we need to erase our candidate right point value and instead take the next value to the left. And similarly, if we have to shorten the segment and we see that there would appear a new element such that it is equal to C, then that would become the new candidate element for that side. So is that clear? Hopefully, yeah. But as we've seen in the case with the frequency array, where was it? Yeah, in the frequency array, we now only have a thing that queries us what the frequency is for an element and whether it is like suitable. We need to have a data structure on top of this to actually aggregate every single information from every single data structure. In other words, we now solve the problem for every endpoint equal to C, but we need to take the minimum over all the subproblems for every single C. So then, new data structure on top of this, look like this. Section, insert an element in the set, erase an element from the set, query, return the minimum element from the set. Then the insertions and the erasures are what happens when we keep modifying these data structures for every single class of equivalent elements, of equal elements. Because if we insert, then the candidate element might shift. It might increase, it might erase, and the value that we have at any point, at any time for the query might change. But we need to have the minimum value that we get by querying either of these data structures. So then we can just keep a set of all the answers to the queries. And then when we notice that upon updating, some query value changes, like we update and it changes, then we need to also update the data structure that contains all the query values. And the data structure is basically what it is, what many people call a heap or a priority queue. But as I previously mentioned, this is not good because then what we will have is the following: updates might take of log time. And queries also take, and as I discussed earlier, that's not bad, not good. Can we find a data structure that still answers these questions, but it's time to update? Maybe more time to query, but most importantly, less time for update. And now it's your turn. I will wait for 2 minutes, see if anyone can give you this. So we just need a data structure that can handle the following operations: insert an element, erase an element, and then query for the minimum element. In stack. I'm not sure what you might mean in stack. Because, we need to be able to insert elements at any given point, erase any single element from the data structure, and then query the minimum element from the set. And normally I know that multi-sets. Multi-sets is that updates still take of log time. Frequency array is a good idea, but the issue with frequency array is that like queries, if done naively, might take all time. Because like you have the frequency array, and well, what you need to find is the first time when the frequency is non-zero. Because it addresses the update issue. But it's not complete yet because we need something on top to get the minimum element much faster than all of them. case of an query, I think. Update is very simple. Either the value at query appears or it doesn't appear, and then we need to find basically the first non-zero value. No, not ordered sets. Sets take a long time for updates. Frequency array is a very good thing. The issue is that most of the nice data structures that we learn to use generally try to balance updates with queries, because it generally is assumed that you have as many updates as you have queries. But this is not true in our case. In our case, we have a lot of updates and not very few, but a smaller amount of queries. So sets, heaps, segment trees, everything, heaps, whatever, they are bad because they take too much time. But frequency arrays are good. I really like frequency arrays. Wait. This is a good idea, I think, but I'm afraid of it, sort of. The reason why I'm afraid of this is that basically what you describe is like DSU with updates, and like normally, so I think you might be referring to the thing where you keep like segments right, and you keep like for the left endpoint what is the right endpoint of the segment, for the right endpoint what is the left endpoint, and then when you erase an element you basically tell the left endpoint that it doesn't exist anymore, and you can simply merge the segments. My issue is that this is a DSU-like problem where, like, if you insert a new element and you need to erase it, how does it know which segment it belongs to? That is the main issue. Maybe last time this element was a left endpoint, it was a left endpoint to this right value, and then erased this right endpoint was then a left endpoint with this, and so on. It's kind of problematic to see how we find a segment that any element would belong to. I really like frequency arrays. Let's go with frequency arrays. Okay, so maybe not frequency arrays, but it will have the same issue that we've had before, basically. But segment trees over frequency arrays are okay. Because what segment trees will do is essentially we'll calculate some sums of values over multiple intervals, and we can basically binary search the largest sum of the largest segment, such that the sum is not such as the sum is still zero. So and a binary search over the segment tree would look like, hey, can I go all the way to the midpoint and every element is still zero? If so, then the element that I'm searching is in the right half. In this case, it's not, it's in the left half. Then, is there any element from in the smaller subhalf? And there is, and so we need to calculate this one more time. Then, is there any element in this half, which we calculate? There isn't, so we need to go into the left, and so on. And it is, and it isn't, and then we finally get to this singular element. I repeatedly binary searching. No, I say erase and insert in of one time, but get min value can be whatever you want, maybe not of n, but whatever you want. So this we want O1, this we want O1, but this can be whatever. Because then the time complexity is of query times have n times square root times the complexity to do an update plus q times the complexity to do a single query. So then we want this to be, this can be big, we don't care, but this has to be small. I will have to now show you the solution, I'm sorry. But okay, the issue with segment trees is that an update takes log of n time. Why? Because every single element is included into log segments. So it's included in this segment, and it's included in this bigger segment, and this bigger segment. And there are like 17 or so segments that we need to update. What if there was just one single segment that we needed to update for every single value? Then obviously, how would such a data structure look like? We claim that the optimal way to distribute elements such that they all belong to a single interval, and it would still do an update on how we can find the first block or first element that is non-zero, would be to divide this number line into blocks of size square root. So if we do this, then for each square root block, we need to keep what is the count of non-negative elements here. And then first, what we need to do is find the first block where this count is not zero. Maybe for this first block, the count is zero. Then we check the next block. Is this zero? Okay, then we check the next block. Is this zero? And if it is, if it isn't zero, then we know that there is a non-negative element. Then we can take the elements one by one in this block and find the first element that is non-zero. So then, and set a bucket finding the first root on zero bucket, and of B finding the first root on zero element of that bucket. And because we said we should try to make these two equal, B is equal to square root of that. So we have a data structure that updates in how much? Well, we need to update when we insert an element. We have to say, well, it exists, and we also have to update the sum of its bucket for the count of non-negative elements. So this O1 and queries in sorry. Oh yeah, it said it maybe before I did. SQT decomposition. Congratulations. I don't really get it, but you said the same thing. Yeah. So the answer is SQT decomposition. That's it. That's basically it. Okay. There are a lot of problems that have algorithm. I'm not going to go through all of them. Okay, that technically is more with updates, but it has to be that or more with no third clause. Technically, one can get rid of this third clause, but I don't want to get into it now. I don't think I'll have time. Because there are maybe more. Very briefly for those that are interested, is that you have a data structure and you first insert the elements of R one by one, and then only afterwards you insert the elements on the left side. And then when you do this, you can basically pop all the elements from the left side
because they're on the top of the stack. So this works for things like DSU. This works for things like DSU. Because at every time, the elements that are most likely to be popped, to be shifted around constantly, are the ones on the left side. So then for the right side, we have a stack. We add elements one by one by one by one. And then when we get to the next query, we add all the elements within that bucket that belong to that query. Afterwards, when we need to go to the next update, we pop all the elements on the left side. We continue to increase one by one by one by one the elements on the right side, and then we again insert everything that we need to on the left side. Then we clear the left side and so on. This is how to do with not close. This is there is no point. But on trees now. Okay, so there are two structures that appear whenever there is a query in trees. There are only two, I think. There are others, but those are a bit weirder and not that common. So there are subtrees. There are paths. These are the two sort of structures that one would want to query on trees, and they come out naturally. I will first talk about how to apply Move's algorithm on paths. How to do this is no matter whether it's simple or not. It would work as follows. So if subtrees, maybe one can imagine right now what Mo on a subtree would look like, because we know that we can take the reorder of the tree, and subtrees are ranges on reorder. So then they are range queries. But paths, it's a bit harder because paths are by definition not a thing that appears in consecutive things in the array. In the preorder, it might jump from one point to another, and it's not really good. To be able to work with trees on paths either way, to find a linearization of paths that can admit a solution, a mode-like solution, we can construct what is called a post-order. Which is what's a version of the Euler tool, I think, and it works like this. So it's constructed as follows. So construct mode. Select mode for every child in it. And then insert node again. Yeah, you insert node one time when you enter it, and insert it again when you get out of it. Unfortunately, I have to draw it, which to see why this works, let's take such a pre-post order and see how it might relate to nodes. So let's start with 1, 2, 3, 4, 5, 6, 8, 9, 10. Okay, I'll say this is A, B, C. What would be the pre-post order if we start from this node? So it will look like this, I claim. 1, 2, 6, 7, 7, 8, 8, 6, 2, then 3, 5, 5, 4, 9, A, A, B, B, C, C. I really should have done this on the document. 9, 4, 3, 1. Okay, so uh, 1, 2, 3, 7, 8, 9. Now the tendency is that because I told you this is the correct solution, to look at some path, some random path, let's say from 8 to 9. And because there are no other clues here, one might think, okay, whatever, let's start from the first 8 and look until the last 9 and see the elements that we have here, or from the first 8 to the last 9. And let's do so. Now, again, just because I'm a very generous person, look at the frequency of the elements that appear, because we know that elements might appear only once, or they appear at most twice in the whole array. So it might be important to see whether elements appear once or twice in the given segment. So it appears twice. 6 appears how many times? It appears once. 2 appears how many times? 1 time. 3 appears 1 time. 5 appears 2 times. 4 appears 1 time. 9 appears 2 times. A appears 2 times. B appears 2 times. C appears 2 times. Now let's group those that appear twice. Notice that 6, 2, 3, and 4 appear once. Drawing, and lo and behold, it's 6, 2, 3, and 4. Well, they are some elements that coincidentally or not coincidentally appear on the path from 8 to 9. The only two elements that, the three elements that don't appear on the path from 8 to 9 yet is 1, 8, and 9. And I claim that actually the elements that you need to the only elements that you need to consider that belong to the path are those that appear 1 time, and every element that appears 2 times is not actually on the path. To fix this, first we need to address the fact that 8 and 9 appear 2 times, and to fix this we can just say that we will go from the first 8, from the last 8 to the first 9. So let's keep it this way because it's a bit more interesting. Elements that don't appear on the path appear 2 times. The reasoning is pretty simple, and it is the following. Assume this is our tree. And we look at the pre-post order starting from this node and ending at this node. Okay, no, those are 2 bad nodes. Let's start with the pre-post order here and end with the pre-post order here. Because we start from the second position when this appears, it means that we basically already visited its entire surface, so we don't care. So then we look upwards. Then we go up to this point. If the DFS would go down this path at this point in time, all the elements will appear 2 times. They will appear once when we go in them and once when we go out of them. But this element, we will meet him only once, and that is when we want to get out of it and want to move further upwards. After the LCA, we go downwards and we meet elements for the first time because this is the first time that they are encountered during the DFS. Then we might go into some subtrees, but because we go in them and we immediately go out of them, every single element from here will appear 2 times. Then continuing up to the node, the only elements that will appear 1 time will be all the elements from the starting point up to the LCA without the LCA, because they appear for the last time in the DFS, because we exit the DFS from them. And then all the elements from the LCA to the second endpoint, because every element on the path will be met for the first time during the DFS traversal. So then, in such a case, we can see that the elements that appear twice, except for 8 and 9, because this happened due to a poor selection of the starting and endpoint of the segment, would be 5, A, B, and C. And this correlates with the fact that 5, we enter in it and then go immediately afterwards in the DFS. And A, B, and C, we go in them and then we come out of them immediately. And they don't actually belong to the path. So then we can just do Mohs algorithm. And for every node, when we encounter it during the Mohs algorithm, we check, is this the first time that we are seeing this element? If so, we insert it in the data structure. If it's the second time, then we erase it from the data structure. Still, I left unaddressed maybe why the LCA does not appear. I think this is visible in this scenario because all the elements that we met were because either it was the first time that we would meet them, or it was the very last time that we would meet them. This is because their entire subtree, their subtree was either complete, completely visited, or empty. But for the LCA, there might be like a bunch of other, like maybe like before we went into this node, or actually right before we went into this node in the DFS, before it was the last time we saw this node, we had to come into the subtree. So then we couldn't have met him when it was empty, because by the time this subtree is complete, then it means that this subtree is also not empty, because there's something in the subtree that was visited. And by the time we get to the first time we ever meet the second endpoint, it's clearly not complete because we haven't finished visiting its entire subtree. So then the LCA, but only the LCA, will not appear in our linearization. So then we have to manually add it to the data structure, but that would be it. I mentioned that the elements might not, they will appear in this order from this element in order up to this element, but because the LCA has to be inserted manually, you can't really do things that, and because you keep inserting and erasing random elements, you can't really do data structures where the order of the elements on the paths matter. That is, you have to treat them like a set, like do something on the set of all the elements on the path from X to Y. Is it sort of clear what is to do? Are there any questions? So again, we need to construct the pre-post order as follows. We start from the first apparition from the last apparition of the first node to the last apparition of the second node. We do Mo, but when we do so, we check that every element that we encounter, we insert it in the data structure if it's the first time. Wait, why did you cut that? Come on. Sorry. Okay. Uh, uh, when we encounter a node for the first time and for our data structure, we'll insert it. When it's the second time, we'll erase it. So yeah, that's basically it. That is more on paths. There are, I mentioned there might be corner cases, and the path is from like, there to decimal. If that you actually do insert the LCA, so you don't actually need to manually insert it because the path contains that LCA. Okay, now on subtree, I mentioned initially this, which is wrong. I mean, it's not wrong, but this is algorithm with maybe of n times, as I said, which let's say it's n, which I said let's not do, but now we will. Updates, which is suboptimal, and we can actually do a bit better. As someone said, I think in the chat when maybe that problem, it might, the problem that he gave you was, someone said it's just small to large. And unfortunately, what I will say here is also just small to large. But this is very important because there are times when I've seen problems with this, but unfortunately I can't disclose them. When the small to large algorithm normally makes sense when you have a set of nodes and like their frequencies and so on. But maybe you need a data structure where you just need to know that these nodes are active and that they exist. And you want to activate them in some data structure. Like for example, some heavy light decomposition. Maybe you want to change the values of some nodes in a heavy light decomposition to have something. Clearly, you can't hold the heavy light decomposition and then merge it small to large. That doesn't really make any sense. But maybe in some problem you do. The algorithm is then the following. So assume you are in some node and your data structure is empty for now. And this is the heavy child. And these are the light children. That is, this is the child whose subtree is the largest. And all of these children have smaller sizes. We know from like from small to large, if we have like a set of elements S and we wanted to merge it to get the set of all the elements by inserting, merging the sets of each subtree one by one, that the final time complexity is of n log n. That is, if at the time when we are in this node, we visit one more time every single node, but only from the subtrees of the right children, this will not be n squared because every node will be visited maybe n times for each node, but actually n times log n. Because every time a node is visited, it is because from the last time it was visited up to this time, the subtree in which it belongs doubles. So let's say this node was visited, reiterated over forcefully when we were in this node, then the subtree size of this node would be A. But then, because we know this in our current node, the subtree size is equal to b, but most importantly, there is a sibling for which the subtree size is greater than a, then it means that b is greater than a plus a. So then the second time that we iterate through this node will be because we are in the subtree, which is double the size of the last one. And because we cannot uh, double the last instance more than log n times, the number of times we will meet each node will be n times log n per iterate over. So when we did this with merging sets, it was because we bijected the size of the set with the nodes in the subtree and that which we merge together. But we can do this basically the same for a data structure that is more-like, that is respects these properties that I said in the beginning. That insertion can be done pretty fast, erasure can be done pretty fast, and you can erase random elements. So then assume that we start like this with an empty data structure. Then let's give this empty data structure to each of the light subtrees, and we'll tell them solve every single subtree. Okay, the problem is to have this data structure have all the elements in the subtree. So we want everything in the subtree. We will recursively solve every single child the same way we did before. We go in it, we give it the empty data structure. When we come back, we manually clear it. Then we solve the heavy child. But after we solve the heavy child, the root will have inserted by recursive assumption all the nodes in the subtree. In this case, we do not clear the data structure. Afterwards, we manually insert again every single node from every single light subtree. So reinsert every node from the lighter subtrees. Then we also insert the root, and by the end, what we have done is the following. We have solved every single subtree, every single node in every single subtree, and we also initialize the data structure to have all the nodes in the current subtree, which is really what everything that we wanted to do. And we did this with a number of n times log n updates. Is that clear? Are there any questions? Okay. I think then that is it for today, unless there is more time and we can discuss some problems on the homework, some other more related problems. But really, as I've pointed out, Mohs algorithm really matters for the following thing. We need to construct a data structure that we can black box, that can respect these three properties. We implement the data structure, we black box it, and then we apply whatever, well, for subtrees is a previously mentioned method, but for segments, we apply this order of inserting and erasing elements one by one. In whatever order we see fit. And that is it. So should we end or should we do another problem? this case, I think that is it for today. No, because we have to end by 5 p.m. So yeah, I guess that's it. So I'll see you tomorrow. Maybe. I hope. Anyway.